Alright, so today we're looking at section 5.6, which is dealing with inequalities in two triangles and indirect proofs. Now remember, inequalities, that's just comparing two different quantities. Which one's greater than, less than, greater than, equal to, less than or equal to. But instead of looking at one triangle as we did in the last section, now we're looking at two separate triangles. So let's start with the hinge theorem. It's our first theorem we're looking at today. And the hinge theorem states, if two sides of one triangle are congruent to two sides of another triangle, and the included angles are not congruent, then the longer third side is across or opposite from the larger included angle. So notice that we have to have two triangles here, and we're comparing different parts. But we start with the information that two sides of one triangle are congruent, another pair of sides are congruent, which leaves an unknown third side. Now what we're doing here is comparing this unknown third side, which one's longer, which one's shorter. But that's not the only information that we're going to have. I do have to start with congruent, 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 but I also have information on the included or in between angles, so these angles right here. Now let's say that, I'll just make up a number, let's say this is 50 degrees here. Let's say that this one is, let's just say 35 degrees. Now since both of these angles are the included angles, they're in between both of my known sides. What this theorem, what the hinge theorem is saying, is that the longer side is going to be opposite the bigger angle. So whichever of these two values is greater, in this case 50 degrees is greater than 35 degrees, that means that I go across from the bigger angle, and that gives me the longer side. So let's say this is side AB. AB is going to be greater than, let's just say CD, because CD is across from the smaller angle. So that's the hinge theorem. In this diagram here, that just summarizes what diagrams I just did over here. So here we have congruent, congruent, second pair of congruent sides. Angle A is greater than angle D, the measure of angle D, therefore side BC is greater than side EF. So that's the hinge theorem. Now we can use the converse of the hinge theorem. Remember, the converse is going the opposite direction. And the converse of the hinge theorem states, if two sides of one triangle are congruent to two sides of another triangle, and the third sides are not congruent, then the larger included angle is across or opposite from the longer third side. Now notice here is basically the same thing, but whereas before I was finding an unknown side length, now I'm working the opposite direction because I have the converse. And now I don't know which angle is bigger, but I do know a side length. Let's say this is 10, let's say this is 8. So the converse allows me to say, well, I know I have congruent side, I still have to have two pairs of congruent sides, but now I know that one side length is bigger than another side length, therefore I go across from the bigger side, and that is going to give me the bigger angle. This is my shorter side, so this would be the smaller angle. So the converse allows me to solve for angles, whereas the theorem allows me to solve for sides. So that's the difference between the two. And that's what this diagram here is stating. I have congruent side, here's my second pair of congruent sides. Since GH is longer than KL, angle J is bigger than angle M. And that's the converse of the hinge theorem. How we can use this is to compare for different given measures. So example 1, we want to compare side TV and side XY. Side TV and side XY. Which of these two sides is greater? Well, the very first thing we're going to check is, can I actually use the hinge theorem? So in order to use the hinge theorem, I have to have two sides that are congruent. 11 and 11, they're congruent, they're equal. I have 10 and 10, they're both equal, they're congruent. So since I have congruency here, I have congruency here, I can check my included angles. And since angle W is 88 degrees, is greater than angle S, which is 81 degrees, I go across from the larger angle, and that gives me the longer side. So I can say that XY is longer, is greater than TV. And that is my answer. I'm comparing the length of both sides. On the flip side, and this would be using the theorem, by the way, because I'm solving for the side length. Now compare this to example 2. Notice here I have all three side lengths, but I do have two sides that are congruent. Segment or side FG is congruent to side ML, they're both 5. Side GH is 7, side LK is 7, so those are my congruent sides. And then I have my third side, FH, and my third side, my second triangle, side FH, MK. And now I can compare these two angles, angle G and angle L. Well, which of those two angles is the larger angle? Well, since FH is 5, that's the longer side compared to MK, I go across from the longer side, and that gives me the bigger angle. So the measure of angle G is greater than the measure of angle L because G is across from the longer side. And this would be using the converse of the hinge theorem because I'm solving for angles and not sides. Now we can use the hinge theorem and its converse to find a range of values for the values in a triangle. So an example of a range of values is like 2 is less than x, which is less than 10. So x can be 3, 4, 5, 6, 7, 8, 9. That's how it would work if we were looking non-decimal numbers, just whole numbers. So how we solve for this is a few different steps. We're going to use triangle MNP and triangle QRS to find a range of values for the values of x. But first, let's compare the side lengths in the triangle. So notice I have my two pairs of congruent sides. So I can use the hinge theorem because I have my included angles. And now I have to determine, am I solving for a side? Am I using the theorem? Or am I solving for an angle using the converse? Well, notice the x is associated with the side length. Here's my x, it's with the side length, so I'll be using the theorem. So I look at my included angles. I have 66 degrees for angle N. I have 71 degrees for angle S. So which side is longer? Is side MP longer, or is side, let's see, MP, it would be RQ. Which side is longer? Well, since RQ is opposite the bigger angle, RQ is greater than MP. So that's my first step. Now let's look at my second step. The second step is to check that all the measures are possible for the triangle. Just make sure that there are a specific range of values that actually work. So what this means is that we have to remember that in a triangle, all sides have to be greater than 0. And also let's keep in mind the triangle inequality theorem, which we talked about last section. But the main thing is that every side has to be greater than 0. So we end up getting two properties from this, or two things to check. first, if I know that side RQ is greater than side NP, well, I know RQ is 24, NP is 3x plus 6, or minus 6. Well, I can substitute that in, and I can write 24 is greater than 3x minus 6, and now I just use algebra to solve. So I'm going to add 6 to both sides. That gives me 30. 30 is greater than 3x. Now I'm going to divide by 3, and I get, whenever you do inequalities, always read it in terms of x first. So this would read that x is less than 10, or I could write it like this: x is less than 10. But I'm not done, because I still have to remember that all sides have to be greater than 0. So the second thing I have to do is say that 3x minus 6, remember this is the shorter side, 3x minus 6 has to be greater than 0. It can't be a negative value, and it can't be a 0 value. So this is my second thing I always have to set up, is the side being greater than, or the angle being greater than 0. Now I use algebra to solve, so I add 6 to both sides. I get 6 is less than 3x. And now I divide both sides by 3. I get that x is greater than 2. Now I can put these two inequalities together for my solution. Just a second. Let me combine both of these. And I'll say that 2 is less than x, which is less than 10. And that is my range of values for x. And if I were to plug these in for the actual segment lengths, I would get that 0 is less than NP, which is less than 24. So this is my values of x, and this is the actual side length, what it could be, which makes sense. Now I can also solve for angle measurements. I'm not limited to just side. This would be using the converse, because I'm solving for an angle measurement. The same process here, just a little bit quicker. First, we're going to say, well, which side is the longer side? Well, this side, 20, is greater than 15. Notice I have congruent, 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 so I can use the converse of the hinge theorem. So I take the longer side, go across, and this will be my bigger angle. So first I'm going to say that 95 degrees is greater than 9x plus 5. And quick note, this is not in your notes, this is just extra. But I say that 95 degrees is greater than 9x plus 5, and then I solve. So I subtract 5, 90 is greater than 9x, divide both sides by 9, and get that x is less than 10. And the second thing I have to do is remember, an angle measurement has to exist. It can't be 0 or less than 0. So I say that 9x plus 5 is greater than 0. Now solving here, subtract 5 from both sides. Now I divide both sides by 9. And I get that x is greater than 5/9. So my range of values, when I combine both of these, my answer, my solution, is that negative 5/9 is less than x, which is less than 10, and this is my answer. Now you might be saying to yourself, I thought I can't have a negative value for x. Well, it's okay to have a negative value for x if, when you plug it back in, you get a positive value. So just because this is negative here, it's okay, because what matters is the actual angle measurement. You can't have a negative length or a negative angle measurement, but you can have a negative x value if, when you plug it into the equation, it gives you a positive value. So quick note there. Now switching gears a little bit, we're going to be looking at proofs again. So far we have written proofs using direct reasoning. So with a direct proof or direct reasoning, we begin with a true hypothesis and we build a logical argument to show that the conclusion is true. It's very linear. A leads to B, leads to C, leads to conclusion. Our new method of proving something is called the indirect proof. This is also going to be referred to as a proof by contradiction, both the same thing, just different names. But with an indirect proof or a proof by contradiction, we begin by assuming that the conclusion is false. Once we assume that the conclusion is false, then we show that the false assumption leads to a contradiction. And if you have a contradiction, then your original hypothesis, the true hypothesis, has to be true. So here are the indirect proof steps. How do you write an indirect proof? Well, step 1, we have to identify the conjecture to be proven. What are we trying to prove? Step 2, we assume the opposite. This is a big step. Assume the opposite, which is the negation. So assume the opposite of the conclusion is true. Now I'll do some examples of this in a second. Then we use direct reasoning. So once we assume the opposite of the conclusion is true, it's just a normal proof, but we show that the negation, this assumption, leads to a contradiction. And since the contradiction arrives once we get to the contradiction, we can say that the assumption is false and our original conjecture therefore must be true. So let's look at how do we assume the opposite. So this is a very important step for indirect proofs. How do we assume the opposite of something? Well, let's start really basic. Let's say that I give you some information and my conclusion, so you're given, you go outside, my conclusion, the sky is blue. That's my conclusion. Well, what's the opposite? How do I assume the opposite of that? The sky is not blue. Let's say I give you a conclusion that Bob is good at baseball. What's the assumption of the opposite? I assume the opposite of that. The opposite would be Bob is not good at baseball. Let's say I give you a conclusion that triangle JKL does not have an obtuse angle. The opposite is triangle JKL does have an obtuse angle. So that's how you assume the opposite of a conclusion. And that is an important step to an indirect proof. So let's do a quick example of how do you write an indirect proof. So here we are given that triangle JKL is a right triangle. We have a right angle here. Let's prove, this is our conclusion, let's prove that triangle JKL does not have an obtuse angle. Hopefully it looks familiar. So our first step when writing an indirect proof is to assume the opposite of the conclusion. And that's the first step after we have our givens. So the opposite is I'm going to assume that triangle JKL does have an obtuse angle, and we're going to pick an angle. I'm going to say angle K is an obtuse angle. Clearly it's not, we can see it, but we're going to assume it. This is part of the indirect proof method. So I assume that angle K is obtuse, and now it's just a normal two-column proof. I'm just going to use direct reasoning. We're going to say that the measure of angle K plus the measure of angle L equals 90 degrees. And this is because in the acute angles of a right triangle are complementary. They add to 90 degrees. I'm going to subtract the measure of angle L to both sides, move it over to the other side. So I have the measure of angle K equals 90 degrees minus the measure of angle L, and this is using the subpo. Then I'm going to say, well, I'm assuming angle K is obtuse. So by definition of an obtuse angle, the measure of angle K has to be greater than 90 degrees, by definition. Well, then I'm going to say, well, look for connecting points. Measure of angle K, measure of angle K. If the measure of angle K equals 90 degrees minus the measure of angle L, I can substitute that in and say 90 degrees minus the measure of angle L is greater than 90 degrees using substitution. And then, where am I? Okay. Then we're going to say, well, let's subtract 90 degrees from both sides. 90 minus 90 is 0. And this would really give you a little bit of math here. The negative of measure of angle L is greater than 0 degrees. I'm going to multiply both sides by -1. Remember, when you multiply or divide an inequality by a negative value, you have to flip your inequality. So that gives you the measure of angle L is less than 0 degrees. So that's how we arrive at this conclusion here, that the measure of angle L is less than 0 degrees. But there's a problem here. We can't have a negative value for an angle. So this is a contradiction. This cannot happen. So since we arrive at a contradiction, this cannot happen, we can conclude that our original conjecture, which is that one right there, is true. So we say that the assumption that triangle JKL has an obtuse angle is false. Therefore, we have proven that triangle JKL does not have an obtuse angle.